So far in our content, we've been talking about this idea of line integrals. And a closely related concept is that of the flux integral. So in this video, I just want to provide a little bit of motivation for what the flux integral is and how we can begin thinking about it. So let's suppose that what I have here is some rectangular surface. And for all intents and purposes at the moment, let's assume that that is a flat rectangular surface. So it doesn't have any curvature to it whatsoever. And this has some area. So let's just say that this rectangular area is, we'll say 2 square meters. 2 square meters. We'll use the metric system in this particular example. And at the same time, this rectangular region, whether this is some sort of net or just some area underwater that we're focused on, we have some sort of liquid flowing through this rectangular surface. Okay, again, this is not like a wall, this is more like a net, something that allows the water to freely pass through. And so we'll say that the water has a velocity. We'll just say that the water can travel at a rate of, we'll say half a meter per second. Now, interestingly enough, if I multiply these two values together, if I say, well, I have water flowing in at a rate of half a meter per second, per 1 second, and I have a net that it has an area of 2 square meters, then I get a quantity that would represent meters times meters squared. This would be 1 cubic meter, 2 times a half, per 1 second. So we've gone from representing something that is a linear motion, right? This is a vector, and it is passing through this two-dimensional surface. So when I multiply a distance by an area, I get a volume, a rate of volume per time. Right? That's what this quantity over here is. It's volume per time. So it's as if each of these vectors sort of represents what is happening or how much water is getting through per second. So if I extended the edges of this and I kind of closed this off, you would see that we would get a three-dimensional solid, specifically a rectangular prism. So everything that's inside of this rectangular prism kind of looks like a box of a television, is considered to be the amount of volume that makes it through that surface in 1 second. So this container is filled with 1 second's worth of water that flows through this surface. We're going to give this a name. We're going to call this flow rate of volume per second, volume per time. We're going to call this the flux. It is the flow rate of, in this case, the fluid through the surface. Now, water and movement gives us a very practical and tangible thing to think about. It doesn't have to be water. This could be dealing with magnetic. We actually have something called flux in electricity and magnetism. I don't know a whole lot about that, but this does not necessarily have to be physical movement of water. These could be magnetic fields as well. So we're not limited to movement through a rectangular region. I could have a circular region. And we can give this thing an area here in just a second, but we can say that we have vectors representing constant velocity passing through this surface. And let's suppose that in this case the magnitude of those velocity vectors, we're going to assume for just a moment that they're constant, that these may be, I don't know, something like, we'll say a little bit faster. How about 2 meters per second? And we'll say that this region that we're trying to measure the flow rate through, maybe this is a pipe. And I'll tell you that the cross-sectional radius of this pipe, we're going to say that this has cross-sectional radius of, we'll say 3 meters, a fairly large pipe. Okay, and what we want to know is, again, what's the flux through this surface? So I would first of all have to get an idea of what is the area of this circular region. Well, that's going to be, let's see, the area of a circle is going to be pi times the radius squared. So pi times 9, so 3 squared. And now if this is measured in, distance is measured in meters, then the area will be measured in square meters. So if I multiply the area times the magnitude of the velocity, I get 9 pi times 2. Now this is meters squared times meters, which is going to give me, again, cubic meters over 1 second, which is 18 pi, which is, let's see, about 18 pi will give me about, I think, roughly about 28, 29 times 2. So about 56.5 cubic meters per 1 second. So that's how much volume is passing through that circular region. Well, now that we have an idea of what flux is, and we can do this for many different shapes. Right now we're assuming that our two assumptions right now. Right now we're assuming that, first off, that our surface is flat. And the second thing that we're assuming is that the velocity, that the vector field for velocity vectors is a constant field. Of course, we know that that's not necessarily true. The surface itself doesn't have to be flat. We will build upon this, but for now, at least we have a bit of intuition behind how this works. So volume per second. Now, in order to start assessing surfaces that are not flat, it makes sense to define a few things. First of all, we're going to want to decide where the flow is, which orientation the flow is in. So for each surface, we could actually have orientation that would be in one direction, perpendicular to our surface in one direction, or in exactly the opposite direction. This is something that we face with the cross product, where depending on what order we cross our vectors in determines the sign of that cross product, or the signs of that cross product. Now we can define the flow. We're not going to get too wrapped up in this, but just keep in mind that at any point there are two normal vectors, one that is in one direction and one that is in exactly the opposite direction. But for now, let's just go ahead and just point that out. Here is just a representation of our surface, and the surface is going to have a normal vector. Remember, the normal vector is going to be perpendicular to our surface. That means perpendicular to our surface. All right, now if we take a normal vector, and let's just suppose that S has area equal to A. It has some area, right? That's the area of this entire flat surface. Then if what I do is I take the normal vector, and specifically not just any normal vector, but the unit normal vector. So let's just say this has unit length, it's 1 unit long. And if what I do is I multiply or scale that unit vector, that if I scale this guy by the size of the area of S, then I get a vector that is going to point in the same direction, but now it's going to be a units long. It's going to be a units long. It could be less than 1 if the area of the surface is smaller than 1. We could actually shrink it down to something a little bit smaller, or we could scale it up if the area of our surface is greater than 1. So what we get here is we get a vector that has two properties. Okay, first of all, it might seem weird that we're going to create an area vector, but it's going to prove to be very useful in more ways than one. First of all, the advantage that this will give us is that the magnitude of the area vector is the area of the surface. Well, that's convenient. The direction of A is the direction of the orientation vector n. So it basically points perpendicular to our surface. Right, so A is going to be perpendicular to our surface. If n is perpendicular to our surface and A is just a scalar multiple of it, then it's also going to be perpendicular to that surface. So this gives us an advantage. We now know basically the orientation or the angle of the surface itself. And this is going to come in extremely important because our flow rate does not necessarily need to be in the same orientation as our surface itself. So look back up here. Here we were kind of assuming that all of these vectors, maybe we didn't notice it, but we were assuming that all of these vectors were perpendicular to our surface. So it was like here is, if we look at it from the side, we were assuming that all of our vectors passed through perpendicularly to that surface. Same thing here, if we were to turn this thing on its side, kind of assuming that all of these flow vectors are perpendicular to our surface. This does not have to be the case. The other situation that we can have arise, to build a little bit of intuition behind what we're going to do, if I were to have a flat surface, if my surface were to run this way, and what I had is vectors flowing parallel to that surface, then you might agree that in this case there's going to be 0 cubic meters per 1 second passing through that surface, right? Because they're actually not passing through it, they're passing along it. So there's actually not going to be any water that actually passes through that netting, if that's what it is. So in this case, what we would see is that our area vector would be, let's think about this, our area vector is perpendicular to our plane, and there's our area vector. Our velocity vectors, in this case, are parallel to our plane. Therefore, the velocity vectors are perpendicular to the area vectors. And so what we would get is that the dot product between the area vector and the velocity vector is 0. So here we have A and V are perpendicular. Notice that we're not really talking about the surface here directly. We're referring to the area of the surface by this vector that is perpendicular to it, which is called A. We have one other scenario that we've considered, and that's been the one where the passing of water has been directly through our surface. So our surface has been like this, and our area vector in this case again points perpendicular to our plane. And our velocity vectors, interestingly enough, point in exactly the same direction. So our velocity vector and our area vector has a non-zero area. Rather, not a non-zero area, a non-zero dot product. So A and V have an angle of 0 degrees, or 0 radians. So if we were to take the dot product between A and V, because they point in exactly the same direction and the angle between them is 0, we would expect that dot product to be bigger than 0. So I'll just say for now not equal to 0. And we'll see how this all connects in just a moment. Now let's consider the more likely case, which is that our plane is actually going to be tilted. So let's say we have a tilted, surface. And again, we're going to assume that this surface is flat for now, but we're going to now consider that surface to look more like this. So now it's tilted. And now we again have an area vector that's perpendicular to our plane. I'm going to draw it as kind of coming inward this way, and now this is perpendicular to our plane, if you will. But we have velocity vectors that do not go in exactly the same direction. They go this way. There are our velocity vectors, and once again, our area vector is here. Our velocity vector are these blue ones, and so we see that there's some angle between our area vector and our velocity vector. So we'll say that we have an angle of theta between A and V. So what problem does that pose? Well, let me draw the two-dimensional representation of this. So let's pretend that we're looking at this from the side. That's our surface right there. And we have velocity vectors passing through this way. Okay, now they're not actually passing from here to here, right? Because that would assume that our vectors are coming in perpendicular to our surface or parallel to our area. So that means they would be passing along this entire length. But the thing is, all of these vectors are passing through horizontally, which means that they only pass from here up to here. Now this is sort of a hypotenuse, if you will, but those vectors are actually only passing along that length right there of this surface. So what that means is that I am going to think about this surface as having this height right here. That way those vectors are actually passing perpendicularly through that height. So if I think about in this 3D sketch here, if I think about this side as representing the length and this is representing the width, so we're actually kind of looking along the length. So this right here is length L, and I'm going to call this right here, I'm going to call this H, because even though my surface has an area of length times width, it's rectangular, I actually will want this length to be, I want this to be height, right? Because it's still passing from left to right along the entire width. All of those vectors are passing from left to right along that width, but they're only passing along, as we mentioned, the distance from the top of the plane to the bottom of the plane. And since it's tilted, its length is not totally relevant. It's actually the height that it has when it is tilted. Now, in terms of incorporating that and figuring out what this height should be, I'm going to draw my area vector. My area vector is perpendicular to my plane. So that's going to be my area vector right there. Okay, now my velocity vectors, we said those are running left to right. So right there, between my velocity vector and my area vector, there's some angle right here called theta. Now, without getting into a terrible amount of geometry here, I can actually use this to establish that this right here is theta as well. That angle right there at the top between where this height of this kind of pseudo prism and the actual length of the prism, where those two lines meet, that's going to be the same thing. A way of thinking about this is if this is a 90-degree angle, The area vector is perpendicular to the surface, so this has to add up to 90 degrees. So this right here would be 90 minus theta, and if this is 90 minus theta and this is 90, then those add up to 180 minus theta, and that leaves this as being theta, so that they add up to 180. In any case, if that's theta right there, and what I want to solve for is the height, I can use the relationship that the cosine of theta is going to be adjacent over hypotenuse. So it's going to be the height divided by the actual length of that tilted surface. Now, what I wanted to solve for is h. So h is going to equal L times the cosine of theta. And now the actual adjusted area, I'll call this the adjusted area, will equal the width, which will be W, times the length, times the cosine of theta. Now, width times length is the actual area. So that's going to be the actual area. Well, hey, by the way, another way of writing the actual area is the magnitude of the area vector. Right? The area vector has a length that is equal to the area of this entire surface right here. So we have the magnitude of the area vector times the cosine of theta. Now that's the area through which water actually passes. So the flux of this surface, the flux of S, of this guy here, will be the area, right? It'll be area times flow rate. Well, the area we just established is the magnitude of the area vector times cosine of theta. The flow rate is going to be the magnitude of the velocity vector, assuming that those velocity vectors are constant, as we have assumed earlier on. Now I'm going to rearrange this a little bit. I'm going to write this as the magnitude of A times the magnitude of V times the cosine of theta. Okay, that's the flux of S so far for a flat surface with constant velocity vectors. Now, I'm going to say, remember that this actually poses an interesting relationship, that from the law of cosines, I have that the dot product between two vectors is equal to the size of x times the size of y times the cosine of theta. So that means that for our problem, that I could actually simplify this considerably. The magnitude of some vector time of A, of magnitude of some vector called A, times the magnitude of some vector called V times cosine of theta. Well, if I work backwards in this equality, that means that that's the same thing as taking the area vector and dotting it with the velocity vector. Now that is pretty cool, and that actually starts to look a lot like a line integral. It's the relationship between where does the area vector point and where does the velocity vector point. So finding the flux of a surface is as simple as finding the dot product between the area vector and the velocity vector, and that is really pretty cool. We, again, could have done this by just thinking about it this way, but what we wanted to establish was this relationship. So as we formally define that, we'll say that if V is constant and A is the area vector of a flat surface, then the flux through surface is equal to the dot product between the area and the velocity vector. Basically, this gives us two ways of being able to find the flux. One is by finding the dot product. If we know the velocity vector and we know the area vector. Let's take a look at an example and see how both of these approaches will work. Water is flowing down a cylindrical pipe that's 2 centimeters in radius. So here we have this pipe, 2 centimeters in radius, with a velocity of 3 centimeters per second. That's how fast the water is flowing through there. Find the flux of the velocity vector field through the ellipse-shaped region shown. Okay, so notice that we have this tilted region right here. The normal to the ellipse makes an angle of theta with the direction of flow. Okay, so that's our area vector and our velocity vector. There's an angle of theta with the direction of flow, and the area of the ellipse is this wacky 4 pi over cosine theta square centimeters. Don't worry too much about that. That's just what we're given as the magnitude of that area vector. Okay, so we can do this in two ways. If we want to know the flux, we can find it by taking the dot product between the velocity vector and the area vector. Now that's one way of doing it, right? But I don't actually have the velocity vector. I only have the magnitude of them, right? I only have how big they are. So unfortunately, dotting them together is not going to work here. But I do know that the other way I could do it is by taking the magnitude of V times the magnitude of A times cosine of theta. So the magnitude of A times the cosine of theta. Now I don't know what theta is. It's just stated as theta. But I do know what the magnitude of V is. That's going to be 3 centimeters per 1 second. Multiplied by A, the area of A is going to be, the length of A, or the area of this ellipse, is given to me as 4 pi over cosine of theta square centimeters. That's the area. And when I multiply those together, I get, well, times cosine of theta. That's this cosine of theta right there. The cosine thetas cancel out, and I'm left with 12 pi, and that's centimeters times centimeters squared, centimeters cubed, over 1 second. Okay, so if I was given the velocity and the area vectors instead of their magnitudes, I could just dot them together. So this formula actually gives us two ways of doing that. Now the other way that I could do this is remember we were just saying that this thing is tilted, so water is not flowing across the entire surface of this. It's only going horizontally through that surface. So water is actually only flowing from up here to down here and everywhere in between. So it's only flowing along the height of this. Well, that's the same thing as thinking about just the circle that has the same height as this guy does. Now keep in mind that the sort of elongated length right there is longer than just the height from the top of this circle to the center of this circle. But I should be able to find the area of this guy here and just multiply it by 3 centimeters per second. So option 2 would be to say, okay, the area of the circle is going to be pi r squared. So pi times 4, which is 4 pi. That's going to be centimeters squared. And then if I want to find the flux, we've already defined that as the area times the flow rate. Since the area is 4 pi centimeters squared and the flow is 3 centimeters per 1 second, that's going to give me 12 pi cubic centimeters per 1 second. So what we've done in this option 2 is we've essentially untilted this ellipse, which in its untilted form would be a circle since it has to fit inside of the cylinder. And then once I knew the cross-sectional area through which water is flowing perpendicularly through, then all I needed to do is multiply that by the flow rate. But if dealing with the area of this tilted ellipse is given to me as 4 pi over cosine theta, if that is the actual area of this tilted ellipse, and it's tilted relative to the velocity vector by an angle of theta, relative to the area vector, then I do need to multiply the product of their lengths by cosine of theta to adjust for it. Now, one last thing to see why this makes sense. If back here we said that if A and V are perpendicular, there's going to be a flow rate of 0 cubic meters per second. Well, now let's think about it in terms of the formula. It's going to be the magnitude of A times the magnitude of V times cosine of theta. Well, the dot product between A and V is 0. A dotted with V is equal to mag A times mag V times cosine theta. But here we have cosine of 90 degrees, which is equal to 0. So it doesn't matter what the magnitude of the area and velocity vectors are. That product is going to multiply 0. And so we see that these two produce the same result. And also, if we have an angle of 0 degrees, cosine of 0 degrees is equal to 1. And in that case, that's just going to be the magnitude of the area times the magnitude of the velocity, which is precisely what we're doing here with option 2. It's like we do have cosine of theta, but it's cosine of 0, and cosine of 0 is 1. There we have flux. Next, we're going to consider how we deal with curved surfaces. What do we do when our surfaces are curved, and perhaps our velocity vectors are not only not constant, but they don't even point in the same direction. Maybe they, at different locations, they point in different directions and with different magnitude. How do we deal with that? Well, it's going to be similar to the idea of a line integral. We're going to find a bunch of these A times V's, and then we're going to add them all up. So we'll do that in our next video.